This is lesson 2.1, relations and functions. The goal for this lesson is to represent relations in various ways and identify the domain and range of a function. So our first investigation question here actually shows a barcode, and we're looking at 13 digits here, and that the last digit is known as a check digit. And we can follow these three different steps in order to figure out how the 12 digits produce that check digit. And the question is it possible for 12 digits to generate two different check digits? So can two different sets of 12 digits have the same check digit? Okay, so there's two different questions being asked here. They're very similar but different. So is it possible for 12 digits to generate two different check digits? So following this procedure, multiply the first 12 digits by alternating ones and threes. So 7 times 3 is 21. Oh, and starting with 1, 9 times 1 is 9. And then 21, 8 times 1 is 8, and so on through each of the 12 digits. Step 2 says to add these all up, so we get 121. And step 3 says subtract 121 from, so go to the next multiple of 10 up from 121, that's 130, and subtract, so we get 9, and there you see the check digit of 9. So the first question says, is there any way for us to get something different other than 9? Using this process? And the answer is clearly no to answer this first question. No, there isn't a different way, because if we're multiplying these values times constant numbers and we're adding their sum and subtracting, there's really no other option besides 1. So we'll call that answer A. And answer B then, can two different sets of 12 digits have the same check digit? Well, 130 minus 121 is 9. Are there any other two numbers that would produce 9? Well, of course there are. If I took 140 and subtracted 131, I would also get 9. So you could see there are lots and lots of different ways that we could reproduce this check digit of 9, or any check digit. So the answer to that one is yes. And what we're going to find out through this lesson is a little bit about what that means when what we'll call this our input, the values that we'll put into this function, and then the output being 9, seeing if that is reproducible or not, will give us a special result. So we're going to look at several key terms in this lesson, starting with pairing. So pairing is literally just doing a mapping. So mapping and pairing are the same. So that's check. We know what pairing is. A relation. So the relation is just the set of ordered pairs. So there's relation for you. Check. Function then, domain, range, vertical line test, function notation, independent variable, dependent variable, and that's it. So many of these you've heard of before, so much of this will be review. So let's look at this key concept box here. You'll see here that ordered pairs, so here it is, input and output. The x's are the inputs, the y's are the outputs. Here's a mapping to represent that same relation. So all of the x values you can see, -3, you see how they're represented in order from least to greatest, that's important. -3, then 3, and then 4. Notice that 4, although it's repeated here in the ordered pairs, it's not repeated. It's not written twice. And then the outputs are also listed. So 4, -1, and 3. Now those aren't listed, 4, -1, and 3. Those are not listed in order, but the inputs do need to be listed in order. And then they're just mapped over. So -3, 4 is represented in the mapping in this way, 3, -1, and then 4, -1, and 4 also goes to 3. The table of values then, again, representing the same relation, just written out in table form, and then finally written as a graph. 4 ways to represent the relation. So these next blanks are going to give us a couple of those definitions. The domain of a relation is the set of inputs, also called the x-coordinates of the ordered pairs. The range is the set of outputs, also called the y-coordinates of the ordered pairs. And a function, here we go, we've crossed off several of those key terms. Now a function is a relation in which each element of the domain, the x values, corresponds with exactly one element of the range. So looking up to this relation, you can see that this element of the domain corresponds to 2 different elements in the range or output, and therefore this would not be a function. Not a function. We'll take a look at an example. Skydiving. Jump. So we have a skydiver jumping out of an airplane. See, he's right here. And they experience free fall. So the photos show various heights of a skydiver at different times during free fall. You can see these pictures demonstrate that here.
You'll need to unlock your iPhone first.
So the question is asking us to represent this relation in 4 different ways. See, the graph is already given to us. So we'll start by writing some ordered pairs here. And when we write this as ordered pairs, we use curly braces and then list out the different ordered pairs. So starting here with 0, 10,000, that would be our first ordered pair. Didn't really leave enough room there. And then our second ordered pair is 4, 9,744. And then next you can see the skydiver has fallen 8,976 feet in 8 seconds, so that ordered pair would be 8, 8,976, followed by the 7,696 feet in 12 seconds. And so, sorry, I said that's how far he's fallen. That's the height he is now off of the ground. That's what's represented here by these y values. So after then finally 16 seconds, skydiver is now 5,904 feet. So 16, 5,904. And then we close those curly braces. So there's representing our relation, just listing out the ordered pairs as a set. The second way then we could do is the mapping. So in our first list, sometimes we just use an oval and write those in 0, 4, 9, 8, 12, 16, 0, 4, 9, 8, 12, 16. And I'll have to make a lot wider oval here, 10,000. 9,744, 8,976, 7,696, and 5,904. And then we just draw arrows and map those. Oh, I put a 9 in there. That one was wrong. So just erase the 9 and put an 8 there. So it's going up by 4 each time. So there it works out. And then we can also make a table of values like we saw in that key concept. So the inputs versus the outputs, or the domain versus the range. So again, listing those out. 0, 4, 8, 12, 16, and 10,000, 9,744, 8,976, 7,696, and 5,904. And then again, these are just associated, so 0 for the x values associated with 10,000 feet. So you can see the free fall happening here in the graph. Nice visual there. Example 2 wants us to determine whether each relation is a function. So for each x value, there needs to be exactly one y value. So you can see the -3 is mapped to a -2. It's only mapped to one item in the range. The 0 is mapped to 7, one item in the range, and the 4 to the 1, only one item. So yes, this is a function. Next, just looking at our relation as a set of ordered pairs. What the key thing to look for here would be a repeat of an x value. So are there any other 4s? If we look through the x values here, and yes, there is a 4. So that means 4 would be mapped to a -1 as well as a 1. So that means this is not a function. Lastly, again, you can see 2 is mapped to 2 different items in the range. So this is not a function either. Here's our last page of notes for today. You can use the vertical line test. So now if we were to see in a graph, there's a quick and easy way to determine if your relation is a function. The vertical line test helps us by seeing whether or not a vertical line, sometimes it's called the pencil test, if you place it vertically, if it hits in more than one spot, that's going to tell us that our relation is not a function. So the vertical line test states that if a vertical line passes through more than one point on the graph of a relation, the relation is not a function. Can only cross once. Use the vertical line test to determine whether the graphs below represent the functions. So let's just use let's see, something very thin for a vertical line. Let's use just a small piece of lead here. So do you see here how it hits in more than one spot? So that means that is not a function. So that one is nope. Here, you gotta go all the way through and make sure that no point hits 2 times, and nope, it doesn't. So that one would be yes, it is a function. It passes the vertical line test. And the same thing here with this one, you can see that it does not hit more than once. So this one again is a function. Next, a function rule is an equation that represents an output value in terms of an input value. So you can write a function rule in function notation. I'm videotaping. Thanks, you too. So let's take a look at a couple of examples here. We can see the output of y, this is what we're familiar with, is based on the input x. So what goes in for x determines what comes out for y. And this is the same exact equation written in function notation. So we read this as f of x, or function f of x equals 3x plus 2. The nice thing about function notation is you can actually insert your input value right into this expression. So f of 1, that's how you read this, is the output when 1 is the input. So the whole thing is the input, or the output, but the 1 is itself the input. So the independent variable, this is pretty common sense when you think about it. The independent variable, that's x, represents the input of the function. And then the dependent variable, formerly y, now we're calling it f of x, same concept, represents the output of the function. It is called the dependent variable because its value depends on the input. So for example 3, we're going to plug in each one of these inputs and determine the output. So f of negative 3 equals negative 2 times negative 3 plus 5. So f of negative 3 equals, well, negative 2 times negative 3 is positive 6, plus 5 is 11. So there's, we'll call that A. And then B, we'll plug in 0. Notice we don't have to write x equals negative 3 because it's already clear from our function notation what the input value is. F of then 0, we plug this in to the same equation. So negative 2 times 0 plus 5. So f of 0 equals 0 plus 5, or 5. Lastly, we have f of 1/4 equals negative 2 times 1/4 plus 5. Negative 2 times 1/4, that's negative 1/2. Negative 1/2 plus 5 would be 4.5. Finally, we'll look at an application question here. Tickets. So we're going to start here. The title is ticket price. So tickets to a concert are available online for $35 each, plus a handling fee of $2.50. Hopefully we've done enough of these. We realize that a variable is needed here to represent the number of tickets. So let's call that variable t. So t equals the number of tickets. The total cost is a function of the number of tickets bought. What function rule means we're going to have to use that f of x notation, models the cost of the concert tickets. Evaluate the function for 4 tickets. So there's 2 parts to this one. We'll start with A, and we'll write out a function. Let's call, we can use f of t as our notation, and then we'll call this 35t for tickets. Number of tickets is $35 each plus $2.50. We'll write 2.5. It's in the terms of just writing an algebraic expression, and then we'll plug in 4. So 35 times 2 is 70, times, and then double that, you have 140 plus 2.5, or 142.50. Now we put the 0 back on there. We're talking in terms of money when we give our final answer.